Is Anika Valaru, and this is my Lab 1 lab report for Physics 2211. So, the purpose of this lab was to observe and calculate the velocity of an object with both a real-time video and a prediction model. So, models and principles involved were Newton's second law, the velocity update formula, and assumptions and initial conditions. So, since we want a constant velocity, we're going to assume net force equal to 0. That also means we're not going to take into account friction. The movement will also only be in the x direction, and positive x is to the left for this lab. So here's the preview. The observed velocity was about 0.44 meters per second, and the predicted was about 0.34 meters per second. So they are similar, but they're not exactly the same, and you can see how this worked out in the graph on the right. Main idea is there's a constant speed and direction, so the initial velocity should equal the final velocity. The observed velocity based on the points found in a tracker app, and a predicted velocity based on a calculated initial velocity should be the same. So the system in this video is a cart used in the video, and surroundings is everything else. So for the process, we set it up with a cart, a meter stick behind the cart, and a stationary camera recording everything. So for the recording, there's initial force to push the cart, and after that, it's free to move. So this is what the setup looked like, and the right edge of the cart matches up perfectly with the right edge of the meter stick. So for the tracker process, I uploaded the video into a tracker app, and I made the origin the right edge of the cart and positive x to the left direction. The basis is the meter stick, which is why we had it in the video. And the length of the video went from after the cart was being pushed, so there's no force acting on the cart, to right before the cart goes out of the frame. To track it, the time intervals are in 1/30th of a second, and I track the bottom right corner of the cart. So every 1/30th of a second, I would click to track the new position of the bottom right corner of the cart. So this is what it looks like, and all the red diamonds here show the different positions of the cart as it moves throughout the video. Here you can see the change in x position over time, which is constant, and the change in y position over time, which should be just a flat line, but I'm human, so I couldn't get it to be a flat line. On the right, you can see all the different points. And for glow script, I set up starting with the starter code given, and I changed the initial force, position, velocity, and time. Here you can see the calculation for the initial velocity, which was taken from the first 2 points in the tracker, which came out to be 0.34 meters per second. Here you can see how I changed the initial position, initial velocity, initial time is 0.2 seconds because that's when there was no longer a force on the cart, and delta t is 1/30th of a second because that's what was used in the tracker app. Here you can see the main two changes are the end time, which is 0.9 seconds because that's about the last point I tracked in the tracker app, and fnet is the zero vector because we don't want any force acting on the cart. So here on the left, you can see each line has 2 points. The first point is the time, and the second point is the x position, and you can see how that graphs in the first graph on the right, changing position over time, which is changing at a constant rate. That can be proven further in the velocity graph, which is just a straight line, so constant velocity. In Excel, I had 2 data sets, an observed data set and a predicted data set, and I graphed each of those individually and combined. So here are the 2 data sets, and here are the 3 graphs, and you saw the combined one earlier. Yeah, so similarities and differences. Both data sets had a positive velocity, and the initial point was the same because that's how I set it up. Differences were the actual velocity value, and for the observed graph, the points weren't exactly on the line, while for the predicted one, they were exactly on the line, and this makes sense because observed isn't perfect calculations. For error, there still could have been a force on the cart. In my first point, I tried to make sure there wasn't, but there could have been still a force acting on the cart for the initial points. There was friction acting on the cart, but because I didn't take it into account, that also could have affected some calculations. There were also camera warps, so camera doesn't record everything like perfectly flat, right? So there will be some things off because of the camera warps. What if, so I made positive x to the left, but if it was negative x, to the left and positive x to the right like it normally is, that would have changed all my x positions and the x velocity to becoming negative. This wouldn't have changed the y values though, because the y positive y is still up. What does it mean? So in the y direction, we only have normal force and force of gravity, so that turns out net force equal to 0. There were no calculations in the z directions or anything, so that's just going to be net force equal to 0. In the x, it's a little difficult to say how many forces and are there, but because I did the experiment, I know it was only pushed once, and I know there was friction, but I'm not counting it. So yeah, overall, predicted and observed velocities were not the same.